In this video, I'm going to look at questions looking at proof by induction, but applying them to matrices. If you've seen any of my previous videos on proof by induction, the setup's going to be very similar. The difference will come to when we have to use our inductive assumption. So as always, I'm going to start by just stating what our claim is. So the example we're given here, the claim we're trying to make is that the nth power of this matrix we're given, -2, -1, 9, 4, we're hoping that that's always equal to 1 subtract 3n, -n, 9n, and 3n plus 1. So I'm just stating the claim so I can happily refer to the claim in the rest of my work and it's clear exactly what I'm referring to. And when we come to using making any assumptions, we can substrate into this claim. It's always useful just to be able to refer back to. First step of a proof by induction is always the same. We want to check our base case, and our base case is going to be whatever the lowest value of n we're interested in is. We're trying to prove for all positive integers n, so the lowest one we could be interested in is n equals 1. So let's consider n equals 1. The left-hand side of that is just our matrix to the power 1, because if we replace n with 1, that power just becomes 1, which obviously is just -2, -1, 9, 4. The right-hand side is the one where we have to do some calculation, but it's not too bad. It's just 1 subtract 3 times 1, -1, 9 times 1, and 3 times 1 plus 1. And when we go through this, as expected, we're going to get -2, -1, 9, 4. So we should now state, so the claim is true for n equals 1. So actually, LHS equals RHS. So the claim is true for n equals 1. So just checking the left-hand side and the right-hand side are equal. That's our start. What are we going to do next? We're going to make our usual assumption. We're going to assume the claim is true for n equals k. Be careful, as always, with your wording here. Don't write assume n equals k. We're assuming the claim is true for n equals k. And we should state what that means in this situation. So in this situation, we're going to go to our claim, and all we're going to do is straight away replace n with k everywhere. So our assumption is that -2, -1, 9, 4 to the power of k is equal to 1 subtract 3k, -k, 9k, and 3k plus 1. That's what we're working from here. Now, we now need to hope or prove that if it's true for n equals k, then it's true for n equals k plus 1. So this is our inductive step now. So we're going to consider n equals k plus 1. And this next line is the bit where you could get away without writing it, but it's really useful just to have for yourself, the target. What are we actually hoping is true? Well, we're hoping that when we replace in our claim n with k plus 1, that this claim holds. So we're hoping that -2, -1, 9, 4 to the k plus 1, because we replace them with k plus 1, is equal to, and I'm not going to worry about doing any expanding here. All I'm going to do is replace all those n's in our claim with k plus 1s. So just leaving in the most of this one, even now, I'm just putting brackets, -k plus 1, 9 brackets k plus 1, and 3 brackets k plus 1 plus 1. Up to this step, if you're happy with other applications of proof by induction, it's probably not too surprising. Hopefully the next step will be natural, but this is where you might have to be a little bit creative. So start from the left-hand side of our target. We're looking at this -2, -1, 9, 4 to the k plus 1. The idea we have to do is to say, well, if we're doing this matrix to the k plus 1, this is the same as just doing the matrix to the power of k and then multiplying by the matrix one more time. This is almost our definition of powers. This definitely comes from our power rules, because if we're doing something times k times something to the 1, we'd get something to the k plus 1. So we're splitting that multiplication like this. Why are we splitting like this? Well, look at what we've assumed. We've assumed that this matrix to the power of k is equal to this. So given we've made this matrix to the power of k appear, we're in a position where we can use that assumption. So the first matrix, rather than writing it still as the power of k, I'm going to go and replace it with what we've assumed. So this is using our inductive assumption in 9k and 3k plus 1 multiplied by this nice simple matrix. At this stage, we now just need to go through and do this matrix multiplication. So there's not a whole lot clever being done here. I'd just go through and be careful with what you're doing. So we're going to go 1 subtract 3k times negative 2. It's going to be minus 2 plus 6k. And then we're doing negative k times 9. So subtract 9k. That's going to be our top left entry. I'm going to give myself a bit more room to work with there. Our top right entry is going to be negative 1 plus 3k subtract 4k. If you're not sure about any of these, you need to go away and just do some matrix multiplication to practice. But this should just be fairly comfortable. Matrix multiplication. Bottom left, we're going to get negative 18k plus 27k plus 9. And our bottom right entry is going to be negative 9k plus 12k plus 1. At this stage, we're definitely not done here because look at our target. It doesn't look like this yet. But at least we've got a single matrix to work with. We've now just got some algebra to go through and do. So it's a proof, so we don't want to make a jump here. Let's do a step of simplification. So this is going to simplify to negative 2 subtract 3k. This top right is going to simplify to negative 1 subtract k. This bottom left is going to simplify to negative 9k plus 9. And the bottom right to 3k. And then plus 1. And now we need to look at what we're oh, sorry, I've made a mistake with my multiplication there. That bottom right should be a plus 4. That was just me being careless with those. But this is the reason we've got our targets, because it helps us catch those anyway on the proof by induction. Even if you do go wrong, you're going to catch it when you go to look at what you're aiming for. Now, we've got this. We're hoping for this. Let's just check that these two things are equal. But it looks like we can just rewrite it straight away. So we just want to rewrite in the form we're expecting now. So let's rewrite this first bit as 1 subtract 3 brackets k plus 1. That should work. This we can rewrite as negative k plus 1. The bottom left we can rewrite nicely as just 9 brackets k plus 1. And this is 3k plus 1 plus 1. So we've got exactly what we're expecting. This was the right-hand side of our target. It's just worth checking. You don't need to write it. But you need to make sure you give your answer explicitly with then replace with k plus 1. You will be docked marks potentially on mark schemes if you don't do that final step. Okay, we're done with all the algebra. We just need to put in our conclusion. So this is where we're going to write those same two sentences we're always writing. So the first step is, so if the claim is true for n equals k, then the claim is true for n equals k plus 1. Note you should have this if-then structure. Avoid writing the claim is true for n equals k and n equals k plus 1. We've made an assumption. We're saying if the assumption that the claim is true for n equals k, then it's true for n equals k plus 1. That's really important to get that structure. And then we can say since the claim is true for n equals 1, the claim is true for all positive integers n. Just a couple of things to review then here. Hopefully, if you've done any proof by induction first, these aren't too much of a surprise in terms of the steps. But first thing, state your claim just so you can refer to it. Go into your base case, consider the lowest value of n you're interested in. Check the left-hand side and right-hand side are equal. This statement, probably one of the most commonly lost marks there, just not being careful with the way you're phrasing. So assume the claim is true for n equals k is the exact wording you should be using there, stating what that claim is, and then considering n equals k plus 1. And then finally, this step here, that's the new one, saying we've got this power of the k plus 1, and we can split up to the power of k times the matrix again, just on its own. You could have done it the other way around. You could have had the matrix times by the matrix to the power of k. That's fine. Even though matrix multiplication is commutative, we can split that up either way. You would have been doing slightly different algebra in terms of the multiplication, but the answer would have come out just the same. And then make sure you get those two lines to your conclusion. Thank you very much.